Hello, welcome back. Welcome to the second lecture on study design and analysis in epidemiology. This is the third part, so this is the third video. And if you're over here, you should have already watched the first two videos in order. So we've just described randomized controlled trials. We've discussed how they are designed and why they are designed in that way. And now we're going to move on to discussing limitations, bias, and variability of results from trials. Just as a reminder, in the first study design lecture, you heard about different types of studies. These are often presented as providing a hierarchy of evidence, reflecting their ability to support causal inference and reduce bias, with observational studies generally providing weaker evidence than experimental ones or trials. Within trials, randomized controlled trials are commonly considered the gold standard for evaluating interventions, because randomization helps balance both known and unknown confounders between groups, as we have discussed. However, the best study design always depends on the research question, as well as practical and ethical considerations. For example, one is not always able to conduct a trial for ethical reasons or because of the urgency with which analyses need to be conducted. Think about the COVID-19 pandemic. Early data on the effectiveness of vaccines was needed to guide policy. In South Africa, observational cohort data from medical schemes or medical insurance companies on their members were used to obtain the first COVID-19 vaccine effectiveness estimates, which were consistent with estimates obtained subsequently from trials. It is possible that a well-designed analysis of observational data could provide more reliable estimates than a poorly designed or analyzed randomized controlled trial. Also, one does not always have a causal question. For example, cross-sectional studies are more than adequate for estimating the prevalence of a condition. At the bottom of this pyramid are case series, which documents the path of a group of people, for example, a group of patients with a condition, called a case report when there's only one person, as well as expert opinion. Outside of this, non-scientific evidence would include anecdotes, and we have heard about how dangerous those can be in our thinking about data lectures. At the top are systematic reviews and meta-analyses, which combine estimates or data, respectively, from individual studies to provide an overall measure. Moving back to RCTs. RCTs, like other studies and any statistical estimation, have their limitations. We will briefly touch on some examples and then talk about statistical error that results from unavoidable statistical variability before we close. One important limitation of RCTs is that the participants are often not fully representative of the broader population. Why is this the case? People who choose to participate in research may differ systematically from those who do not, for example, in health status, health-seeking behavior, or motivation. In addition, studies often include exclusion criteria for safety or ethical reasons, such as excluding pregnant women or excluding individuals unable to provide informed consent. As a result, findings may not always generalize perfectly to real-world populations. As already mentioned in the Thinking About Data lectures, when thinking about study results, it is useful to separate three concepts: truth, bias, and random error. Ideally, our estimate reflects the true effect that we want to estimate. Bias refers to systematic errors that move results consistently away from the truth, while random error reflects natural variability due to sampling and chance. Larger sample sizes generally reduce random error, but variability is also influenced by factors such as how variable the underlying population is and how accurately measurements are made. Importantly, increasing sample size does not remove bias. In fact, a very large study can still produce a very precise but biased estimate, as you saw in the second lecture on thinking about data. Although RCTs are powerful study designs, they are still vulnerable to many of the same biases seen in observational studies. Information bias can arise when data are inaccurate or misleading. For example, participants may not accurately recall behaviors, such as how many hours they spent at a computer during the previous week. And misclassification can also occur when diagnostic tests are imperfect and incorrectly classify disease status. Selection bias may arise if participants are lost to follow-up in a non-random way. For example, in studies of viral suppression amongst people living with HIV, individuals who are sicker or less virally suppressed may be more likely to miss clinic visits, leading to missing data that are not random. Researchers therefore try to minimize these biases through careful study design and conduct, including using standardized and validated measurement tools, having clear study protocols, and training staff and evaluators. The goal of a statistical analysis is not only to estimate an effect, but also to quantify the uncertainty around that estimate. For example, we might estimate that time to treatment failure is 1.4 times longer with drug A compared with drug B, with a 95% confidence interval from 1.2 to 1.6, which in some way provides a range of possible effects suggested by our data. More technically, in 95% of experiments, the estimated confidence interval will contain the value we are estimating. Statistical analyses may also involve hypothesis testing using p-values, which help us understand how confident we are about, in this case, the drugs resulting in different times to treatment failure. A p-value is a probability from 0 to 1. It is the probability of observing results at least as extreme as those seen in the study, assuming that some null hypothesis is true. In this case, the null hypothesis would typically be that there is no difference in the drugs with respect to the outcomes. That is our p-value answers. If there were no differences between the drugs, how likely is it that we would have seen this difference in times, or something even more extreme, just by random chance? A small p-value says this is unlikely, and so our initial assumption is probably wrong, and we think the drugs are probably different in terms of the outcome. With a small p-value, there is evidence that the treatment may impact the outcome, and we think we have made a discovery. A large p-value says that this data is quite possible under our initial assumption, and so we still don't know whether the drugs are different. With a large p-value, there is a lack of evidence that the treatment impacts the average outcome, and we still do not know. It is not considered good statistical practice to choose some cutoff to decide whether a p-value represents a result that is significant or not. On any given study, though, we may make the wrong conclusion, and let's talk more about these errors. The analogy we are going to use is looking for planets. Suppose that we are using a telescope to try to discover a new planet, and so the telescope is like a statistical test. When deciding on how to frame the statistical test, the interesting result is usually the alternative hypothesis. In this case, our null hypothesis, or our initial assumption, is that there is no planet where we are looking, and the alternative hypothesis, or what we are hoping to discover, is that there is a planet where we are looking. Let us start with the case that there is no planet where you are looking. If you do not see it, this is correct. But if you do think you see a planet, this is a false discovery, also called a false positive error or type 1 error. Let's consider the case where there is in fact a planet where you are looking. If you do see it, this is correct. You've discovered something, and the probability that this happens is called your power, denoted by 1 minus beta. If you don't see it, you remain unsure, and this is called a false negative error or type 2 error, usually represented by beta. Ability to see the planet depends on a few key factors, such as the resolution of your telescope, the size of the planet, and the weather. The resolution of your telescope, in statistics, is like your sample size. With a higher resolution, you can more clearly see the night sky. With larger samples, you can more clearly measure what you're trying to measure, and you have more statistical power. The size of the planet is like the effect size in statistics. If the planet is larger, if it is there, you should be able to see it more easily. Larger effects, this is differences in outcomes, are easier to detect, i.e. increased power. And the weather represents variability in the data. If you are working under good weather conditions, everything can be seen more clearly. If not, everything is more fuzzy. More noise or variability in data makes detection harder, while lower levels of variability increase power. Moving on from statistical errors, in well-designed trials, the statistical analysis is pre-specified in a statistical analysis plan, written before looking at the outcome data. This plan defines key elements, such as the primary and secondary outcomes. It provides a sample size justification, and it explains how missing data will be handled. It also describes possible protocol deviations. Having a pre-specified plan is important because without it, even unintentionally, researchers may be influenced by the observed data when making analysis choices. This can lead to data-driven decisions, such as trying multiple models, changing outcomes, or selectively reporting only favorable results, referred to as data fishing. These practices can inflate false positive findings and undermine the credibility and reproducibility of the study. A key principle in a trial analysis is the intent to treat approach, where participants are analyzed in the groups to which they were originally randomized, regardless of adherence. This preserves the benefits of randomization and avoids reintroducing confounding that can occur if participants are reassigned based on post-randomization behavior. We have now covered all of the content in this lecture, and I would like to bring it all together now before we end. You may be wondering why we are talking so much about data, when the overall goal is to understand infectious disease mathematical modeling. You will be learning more about modeling in later lectures. For now, I will briefly mention some examples of how RCTs and data from epidemiological studies in general are relevant to modeling. Data from RCTs can be integrated into mathematical modeling approaches, for example, by providing relevant inputs for models. In turn, models can sometimes help inform the design of trials, particularly in infectious disease settings. In infectious disease settings, individuals are not independent, since each individual's status, that is, whether they are infected or not, affects other individuals. This makes mathematical modeling a valuable resource in the analysis and interpretation of trial data for interventions against infectious disease, because it can translate what can be learned in a trial involving individuals into what we expect at a population level in the real world over time if the intervention were introduced to the population. Here, standard statistical methods that typically assume independence at some level are often not sufficient. Taking our learning objectives into account, let's summarize what we've learned. Randomized controlled trials, or RCTs, provide us with causal evidence, while observational studies generally provide us with associative evidence. RCTs greatly reduce the chance that confounding is present in a study, where confounding occurs when the estimated association between an exposure and an outcome is not the causal effect, because of backdoor non-causal paths between the exposure and the outcome. And RCTs generally achieve this via randomization of treatment assignments, where treatments are randomly assigned, and having appropriate control arms for comparisons. Masking or blinding, which is hiding treatment assignments, can greatly reduce bias in RCTs, as well as the use of placebos, which are non-therapeutic treatments. Oversight preserves the integrity of the research and protects participants, and ethics is core to conducting clinical trials. RCTs, as with other studies, are also prone to bias and variability and error in findings, and all studies and analyses should be designed and conducted in a way that adequately reduces bias and variability. Modeling can be used to translate RCT findings into estimates of real-world impact at a larger scale. We acknowledge the support of our funders. Thank you for listening.